This is a short movie that demonstrates the process for calculating the linear magnification of published images. Now, I want to be clear, you would only use this technique when confronted with published images. We would never use this technique when working with a microscope. Now, I'm going to introduce the formula magnification is equal to image size divided by actual size of specimen. And these two need to be in the same units. There are other mechanisms by which you can do this work, but I'd just simply like you to remember the formula. Magnification is equal to image size over actual size. So to help you remember this formula here, is it will boil it down to M is equal to I over A, the MIA formula. Remember that both the image size and the actual size need to be in micrometers for this calculation to function properly. So here it is. It's the MIA formula. Image size and actual size are both in micrometers. This micrograph of pollen grains, I'm going to show you how to calculate the magnification of the image. Now realize that everything in the image is magnified equally. So if someone were to ask you what's the magnification of the pollen grain, it really wouldn't matter what structure you chose here to measure in order to determine the magnification of the pollen grain or any other structure in the image. So for example, right here is a scale line. This line is given as 10 micrometers, and we're going to use this scale line, we're going to measure this scale line in order to determine the magnification of the entire image or the magnification of any structure in the image. So let me bring in a ruler, and it's a little hard for you to read this because of the contrasting colors, but this line, the scale line, is 3.5 centimeters. Okay, now with 3.5 centimeters as the image size and a known actual size of 10 micrometers, we're going to use those two values to calculate magnification using the MIA formula. So we plug in 3.5 as our image size. Now remember, that is the length of the scale bar in the image. Okay, and it was given as an actual size of 10 micrometers. Now it's important at this point that we have our units be the same because they've got to cancel in order to have a magnification value that is effectively unitless. Okay, so we convert the 3.5 centimeters to 35,000 micrometers. You need to remember that there are 10,000 micrometers in each centimeter. 35,000 divided by 10 gives us 3,500. The image, or any structure in the image, is magnified at 3,500 times. With this micrograph of a human hair, you have a chance to practice the calculation of linear magnification. Some information is given to you by the presence of this scale line right here. What I'm going to do is measure that scale line in centimeters, and with the two pieces of information, you ought to be able to calculate linear magnification. The length of this scale line is 2.2 centimeters. What I'd like you to do is take the information given to you and calculate the magnification of this image. Now with this micrograph of Golgi in Euglena, in fact there are two Golgi here, one looking top down and then a cross section of Golgi here, we have the opportunity to practice the calculation of the linear magnification of the image. Now we're provided some information right here because a scale line is given with an actual length value of 0.1 micrometer. What I'm going to do is add another piece of information by measuring the length of this scale line in centimeters to be 3.2 centimeters. So with the two pieces of information, the actual size of the scale line and the measured length of the scale line, I'd like you to calculate the magnification of this image. You can rearrange the MIA formula to determine the actual size of an image when given the magnification, as you can see here. The algebraic rearrangement is quite simple. Actual size is equal to image size over magnification, AIM. Now I'm given 80,000 as the magnification, so I have a known denominator here for the mathematics. What I need to determine is the image size value for the numerator. Now I'm just going to choose a structure in the image. I'm going to take my ruler and I will measure the diameter of this vesicle, which is just pinched off the ER. And it's a little hard for you to see again because of the contrasting colors, but the diameter is 1.6 cm. So my numerator here for image size is 1.6 cm. My denominator is 80,000. Let's take a look at the mathematics of this. Again, you can see here's the original formula, MIA. Simple algebraic rearrangement gives me actual size equaling image size over magnification. I have plugged in 1.6 cm as the diameter of the vesicle. I'm interested to know the diameter of the vesicle in micrometers, not centimeters, so I convert 1.6 cm to micrometers here, remembering that there are 10,000 micrometers in each centimeter. So I have 16,000 micrometers in my numerator divided by 80,000. The diameter of that vesicle is 0.2 micrometers. Here's a chance to practice determining the actual size of this particular image. This is a chloroplast, a micrograph of a chloroplast, and we can choose any dimension of this structure to measure. You're given some information in the image, take note of that. What I would like to do is I will use a ruler to measure the width of the chloroplast, and that's 9.6 centimeters. So what I'd like you to use is the information given in the image and this measured width of 9.6 centimeters to determine the actual width of the chloroplast.